Hello, I'm Regina Rowland, and I am introducing to you ReSTI Course 5.3. This is in the module of Innovation in the Business Context, and the course is called Towards Sustainability, Introduction to Nature-Based Innovation Practice. I want to remind you that we are offering the 5-door approach to e-learning. That means that you can go through this content in any sequence that you like. We are proposing a sequence in case you're not comfortable with that much flexibility. But in the end, the purpose is for you to pass the assessment door and pass the test, which will then demonstrate that you have learned and digested the material. The first step is always to watch this introductory lecture, which will help you understand all the parts that will be addressed in the course in much more detail. So this lecture is about introducing you to bio-inspired innovation. And innovation is a process that actually has to be experienced, that has either as a participant and or as a facilitator. And so while we're giving you a lot of information about innovation theories and practices and processes and methods and tools and outcomes, the class mainly asks you to do innovation, like to take the steps and figure out how to go from a problem state to come out with a solution. And in particular, we are proposing the biomimicry framework and the biomimicry practice. So this lecture will let you know the basics of the framework, the 3 essential elements of biomimicry. We'll also introduce you to the biomimicry thinking innovation process, which has 4 steps, and introduce you to the 6 master life principles of the practice. So what is biomimicry thinking? What is biomimicry in general? So biomimicry was developed by 2 female biologists from the United States, Janine Benyus and Dana Baumeister. And they have been working on this for many, many years, over a decade actually. And Janine wrote her first book on biomimicry in 1997. This was actually the first step when it was published, but those 2 women have been at this for their entire lives. Biomimicry is a transdisciplinary innovation process that involves the disciplines of biology, ecology, design, and then any discipline that relates to the problem state. In this case here it mentions technology, but it could also be a social innovation or innovations that apply to other disciplines. The mantra that we use is that life creates conditions conducive to life. So any innovation that we are producing should do the same. It should create conditions that are conducive to life. The 3 essential elements of biomimicry are reconnect, emulate, and ethos. So I'll be going through these to help you understand what they're about. So reconnect has to do with being out in nature and reconnecting in your mind, in your heart, and in your physical existence to nature. So it looks like this. We go out with biologists or ecologists or naturalists that show us how organisms live, survive, and thrive under the operating conditions on this planet. Emulate is a fancy word for mimicking, copying the strategies that nature offers or that nature uses, the organisms use in order to survive and thrive on the planet. So we look to nature as a model. And that means we find out what these strategies are for survival and how specifically nature is doing that. We're looking to nature as a mentor. So we're not looking to nature as something to use. We're looking to nature as a teacher in this process. We're looking to nature as a measure. So the biomimicry process has a sustainability mandate. And these are the 26 life principles that have been defined as the patterns of nature that make things work here on the planet. and they are also our benchmark for sustainability. We emulate nature, informs processes and systems. Here's an example of a form. On the left, you see a spider web and a spider sitting there waiting for prey, most likely. And on the right-hand side, you see a biomimicry innovation by a German company called Arnold Glass. And the product is Isolar Ornilux Vogelschutz bird protection glass. And so the problem that these people were faced, these designers and innovators were faced with, is the fact that 300,000 birds die every day flying into high-rises in Europe alone. And so they wanted to find a solution for that. And they used the biomimicry process and went out into nature and looked at what's there and how birds interact with those elements. And they found that they do not fly through spider webs. When to us humans, so in our human eye, we can't see these spider webs unless they have water pearls on it, like in this picture here, most likely after rain. And what we discovered is that birds and bees can see ultraviolet light, which is a material that's woven into the spider web by the spider in order to protect their web, most likely. That's part of the evolution, how nature has done it. And so we learned that we could use this ultraviolet fiber in glass, which would then not obstruct the human eye from seeing through the glass, but it would protect the bird's eyes from not seeing that there's a barrier. And so this solves the problem by 99% and is now a product that's out there on the market. So that was an example of form. Here's an example of how we emulate nature's processes. This is a picture of coral reef, of course, and we're looking here at the coral reef structure, which is a very hard material that's seemingly built from nothing, but it is in fact built from the dissolved CO2, so calcium carbonate, in the ocean water that gets combined with materials that the organism itself, the polyps organism itself, create. So on the right-hand side, you can see a product, concrete, actually, from a company called Calera Cement. This is a US-based company in California that has figured out how to use CO2 waste product in order to create their concrete. And their concrete, when it hardens, does not emit toxic gases, which normal concrete does, and also sequesters CO2 throughout its lifetime. So it uses CO2 in form of calcium carbonate in the creation, in the hardening, and in the curing and its lifetime throughout its existence. It is also an amazing product, and it is an example for emulating a process. Here is emulating a whole system. On the left, you see an estuary, and an estuary is a place where two ecosystems meet, and whenever two ecosystems meet, you have amazing magical things that happen that can't happen in either system or anywhere else in the world. And so here, an estuary is a meeting place of fresh water and salt water by a river running into the ocean and the tides bringing in the salt water at regular intervals. The organisms that live in this estuary have the capacity to clean the water of a multitude of components. And a US-based company, John Todd, developed the Echo machine, of which you see a picture on the right. And this is a sewage system where sewage is pumped in and then pumped through these particular containers that you see here that emulate, mimic, copy the way nature cleanses the water in an estuary. And at the end of the sewage system, in the last container, when the water comes out, it's actually drinking water quality. So this was an example of how nature emulates a whole system. I mean, how we emulate nature's systems. The biomimicry thinking innovation process has 4 phases: scoping, discovering, creating, and evaluating. So I'll be introducing you to each of those 4. Scoping starts with trying to understand how the problem is created, what the elements are that feed into it, how these elements are interrelated, and who the actors are in the system, in order to determine where leverage points are. Leverage points are opportunities for interaction, for applying a solution that has an optimal effect. Because you could go into a system and apply a solution, but if you don't apply it in the right point, you might be wasting your time and resources because the impact is so low, so low that it doesn't have the desired outcome. Then once you understand the system, you continue the conversation to determine what the actual function is of the solution that you want to innovate. And by function, we really mean a verb, something that the solution is supposed to do. Because when we look for things, completed solutions, we would have very a limited range of options to work with, except when we look for what the solution is supposed to do, we have a lot more models to look for in nature. Because then we look for strategies, how a certain function is done in nature, where we can look at a multitude of organisms and then combine these strategies for our purposes. So here you see people discussing the problem situation, the function the solution has to have, and also the design criteria, which include the life principles. So out of all the life principles, we then choose very particular ones, 3 to 5, that are very important for this particular solution. And we track those as design criteria throughout the innovation process. Discovering means that we take the function that we have defined in the scoping phase and biologize it. And then we look to nature and say, hey, nature, how do you solve this problem? And we do this in multiple ways. So we actually are out in nature, learning with a biologist or an ecologist or a naturalist who helps us understand how things work out there. But we also look into online sources. We do research with experts. We ask experts to help us understand certain things. But it's really a transdisciplinary process. The outcome at the discovering phase at the end is actually what we call a function card. And here you see the example of a function card, which lists, first of all, the function we were looking for. And it's usually a sub-function from the more general function that we defined in the scoping phase. And for this function, we find the strategy that the organism does. And then we find the mechanism for the strategy, so which is just how the strategy was done. The strategy is how the function is done, and the mechanism is how the strategy is done. So we kind of like spiral down deeper and deeper to find the original magical formula for solving this problem. And on the function card, you see a picture of the organism. So here's a glass sponge, and on the right-hand side, you see a diagram of the particular strategy that we were looking for. That this was a function card for the innovation of a very particular elevator. And we were looking at how the sponge does it so that it has such a light weight. Like if you pick up one of these glass sponges, it's as light as a feather. But it can withstand very strong current in the ocean. And it actually catches its food by funneling smaller organisms that slip through the holes in the glass sponge, and then they can't find their way out. They stay as food inside. This is actually hollow in the middle. But what we really were interested in is the strong structure so that you can withstand wind and current and all kinds of other forces that might racky around otherwise, but without being very heavy. And so we looked at the crisscross structure that is present here, and then we turned the mechanism for the strategy into a design principle. And then that design principle is moved forward into the creating phase. And then the people that show up at the design table, the innovation table, come from multiple disciplines again. They may or may not include those researchers that came up with the functioning part and the design principles, but they followed those design principles and the other design criteria that were defined in the first phase, the scoping phase. So here's some pictures of what a creation phase might look like. We play with shapes in order to figure out how we could use the strategy to build the solution that we're looking for. In this case, the solution was a 3D object, an elevator, so to speak, but it could also be a concept for a whole system or a way how we work together, so it could be very abstract. It could also be very concrete. So other pictures. This was a cleaning station for an animal farm. And then we also evaluate. So the evaluation is the benchmark to make sure that the innovation is sustainable and follows the 26 life principles, and also fulfills all the design criteria that we had defined in the first part. So now we know that the practice includes reconnecting to nature physically, individually. It includes a process with 4 phases, the emulate aspect, so that's the biomimicry thinking innovation process. And now let's talk about ethos, which is the philosophy of biomimicry. And ethos is the mandate for sustainability here. And it is manifested in the 26 life principles. So this is the life principles wheel, which lists all the 26 life principles, and they are organized in 6 master life principles. In the course, you will learn about these in detail, but right now we're just looking at the 6 master life principles so that you can get an overview of what this is all about. So here's one of them. Be locally attuned and responsive. So obviously this is a beautiful picture of an owl fitting into its environment. This life principle is about finding a way to fit into the conditions into which you were born or in which you live. This is also true for us humans, and we haven't done a very good job with that. But this is the life principle, and it invites you to find a way to fit in what is, not to change the conditions, which is what we usually do. Here's another master life principle, be resource efficient in material and energy. And the image here is of honeybee combs. And so these are the hexagon shapes that you see. And what we know about this shape is that it is the most efficient shape. So if you had squares in here, instead of these hexagon shapes, you would get less compartments. So it's efficient in terms of space, efficient in terms of material and energy, because it's also a very strong shape, stronger than a square, for instance, or a cube. And so you can use less material for the walls between the compartments. The next one is adapt to changing conditions. So this is a picture of a ptarmigan. This is a bird in North America that changes its feathers, so the color of its feathers. In the winter, it's all white, obviously to protect it from prey, from becoming prey for predators. And in the summer, it's completely brown, and in the spring and the fall, it is checkered, like you see it here. So adapt to changing conditions. In our human world, we usually try to change the conditions rather than adapt ourselves to the changing conditions that we can't change. Use life-friendly chemistry is another very strong principle in nature, in that we can't say that it doesn't create toxins. It does, but when it does, it uses it for very particular things, like to protect or to get food. But other than that, nature uses a very limited amount of materials from the periodic table. And it creates things in water, it creates things without having to use toxic material. So the example here is, of course, a peacock, and we can see the peacock in its beautiful wheel that it has thrown for us. And you see these brilliant, gorgeous colors. You might be surprised that the only pigment here is brown. The other colors are created by the structure of the feathers, the components of the feathers, and how they're oriented towards the surface. So the color that you see is created by the way the light ray hits this structure. And that's an amazing formula for creating non-toxic and without heat, beat, and treat color, which is not what we do. We use heavy metals and very strong toxic processes that require a lot of energy on top of also being toxic to us and other organisms on the planet. Evolve to survive is another life principle, and that means that nature has in its life formula built in a process where it learns by changing the formula occasionally. And so here in particular, what you see is an egg, and all life forms have an egg or some form of a seed that contains the secret of life, that it passes on through this to the next generation. And so for us, this would be the DNA string. And which genes get expressed is prescribed in the formula. Occasionally, however, mistakes are made to really explore what could happen if such and such is different. Many of these explorations are not successful. They don't help us in any way. But when they are successful, they actually present a huge advantage to survive and thrive on the planet. This is what we know from our history. So for us in human systems, this means to continuously learn and evolve and not sit still, but go with the flow, so to speak, and accept mistakes as opportunities to learn. And when you have an orientation like that in an organization, what might happen if you don't try to hide a mistake or if you try to avoid a mistake? Of course, there are situations where you can't make a mistake, like designing a rocket or an airplane. There you have to have safety built into it, of course. But in other ways and forms, it is of advantage when you allow a mistake to be a vehicle for learning. For instance, the Post-its. So Post-its have this kind of like sticky in the back that you can stick onto something and pull back off, right? And you can stick it back on. This was actually created by a 3M company that made a mistake on the glue sometime and then noticed that, hey, this doesn't really stick the whole time, and it doesn't stick the way we wanted it. But then there was like, well, what else could we use this phenomena for? And this is how the Post-its were developed. So that's only one example what can happen when you allow mistakes to lead your learning. Integrate development with growth. So this is obviously a picture of an embryo in a mother's womb. It's actually my grandbaby. She is now 1 year old. But the idea here is that nature doesn't build a body and then puts a brain into it. It actually builds a part of the body and then the neural pathways to do something with that part. Let's just imagine it creates fingers and then the neural structures to do something, to move those fingers. When you move the fingers, it creates more neural structures which allow you then to maybe move the whole hand. When you move the whole hand, it builds new neural structures and maybe for the arm to develop something. And so while this is a very simplified explanation of how an embryo grows, the point here is that development and growth, so growing in size and developing in depth, in this case, bones and flesh and material, physical material, with the neural structures that guide how these materials can be used. This happens sometimes simultaneously and sometimes one after the other, but it happens in a step-to-step process, in an integrated way. That's the point. This means for business, for instance, that you don't create something like a factory and then figure out, what do I do there? Or you don't create a structure for something that hasn't happened yet. So you kind of like take baby steps. You build from the bottom up, so that you don't create something that then is a problem for you. That's what this means. So these were the 6 main master life principles. And the 26 life principles could also be considered the alphabet of life, which is another project that we're part of, that is going to be introduced to you in the material. And the mantra that we want to remember about biomimicry is that life creates conditions conducive to life. So if our innovations do that, we'll actually be way more sustainable than what we have been doing so far. Let's review. Nature is resource efficient, adapts to changing conditions, is locally attuned and responsive, uses life-friendly chemistry, integrates development with growth, and evolves to survive. So resource efficient, adaptable, locally attuned, life-friendly, integrated, and evolving. This is the kind of innovation that you will learn in this course. And in summary, this lecture introduced you to bio-inspired innovation, to the biomimicry framework with its 3 essential elements, the biomimicry thinking innovation process with its 4 phases, and the 6 master life principles. I would suggest that next you go to the library overview document, which orients you to all the resources that are available and also has a suggested sequence in case you're not so comfortable with the free flow through the 5 doors. Just want to leave the credits up for a moment so that I thank properly all the people involved in creating this material. And I wish you much fun with this course and a successful completion of it. Bye-bye.